Hi, everybody. Welcome to Chapter 2. So, the reason we go through chemistry, even though this is a biology class, is because you have to understand the chemical level of organization to understand how things work. Because in general, the majority of the reactions occur in a fluid environment, and you have breakdown of macromolecules into smaller monomers, which is a chemical reaction, and then you have buildup of other molecules, another chemical reaction. So the more knowledge of chemistry that you have, the easier it'll be to understand how a healthy diet or medications can be used to treat patients. So I always start with, what is matter? Matter is anything that occupies space and has mass. So the air that we breathe is composed of matter because it occupies space and has a mass. You are composed of matter. Matter can be found, Matter can be found in 3 different states: solid, liquid, and gas. And I like this picture that I got off of Google Images because it shows water in all 3 phases. Not all substances can be found in all 3 phases, but water can. Water is solid as ice, liquid is water, that's what it's called, and gas is water vapor. So let's look at what energy is, because everything that occurs in the body has to have some energy to provide the ability for work to occur. So energy in a nutshell is the ability to do work and bring about change. Energy doesn't have mass. It does not take up space. But energy can be found in different phases. You can have energy that is called kinetic energy, and that is energy of work. That is actual work occurring, movement, motion. Whereas potential energy is inactive or stored up energy. Think about the cup of coffee that might be sitting at your table, or the sandwich that you might be getting ready to eat. That would be chemical energy that is also called potential energy. Whereas kinetic energy would be the energy that's already working. So like the movement of the body, that's kinetic energy. So let's look at 3 types of work that are over here. We have chemical work, where we have ATP drives the buildup of molecules A and B to produce AB. Here we have transport work, where we have ATP driving the pumping of ions from a lower concentration to a higher concentration. And here we have mechanical work, where we use ATP to cause muscle contractions to actually move, in this case, maybe move materials through our digestive tract. There are lots of types of energy. The ones we typically talk about in A&P are chemical energy, which is energy stored in chemical bonds. That would be that sandwich that I mentioned. Electrical energy, this would be this would be a driven form of energy using the electrolytes in our system. So this is how our nerves fire, and actually how our muscles work. Mechanical energy is directly involved in moving the body or moving materials throughout the body. And then radiant energy. So this is not a form of energy we typically talk about in A&P, but radiant energy is the rays, sun rays coming down, and the energy that is given off, which is actually what is used in photosynthesis and brings the energy to Earth, because the sunlight is the ultimate energy source. We're going to talk about the different elements that make up matter now. So energy, or I should say energy is not composed of matter, but elements are the units that make up matter. And in the body, we have 4 major elements. We have oxygen, carbon, hydrogen, and nitrogen. And so I have a table. Hold on. I thought I did. There it is. This is a periodic table that shows all the elements. So I'll show you this in a little bit, but this shows the carbon here. Oh, it doesn't have every element because it's kind of cut off. I'm sorry. There's carbon, nitrogen is right here, oxygen would be over here also, a couple rows over, and hydrogen would be on this side. I didn't realize it was cut off. Here are the majority of elements that make up the body. Again, I told you oxygen, carbon, hydrogen, and nitrogen make up the majority of the body. So if you add all these together, that's like 90-some% of the body. But we have a lot of elements that make up a very small amount of the body, but without them, we would not be here. This video here is a fun video for you that you can watch. I'm not going to play it. Playing a video in a video is not a good idea. It doesn't sound right, and it actually would be against copyright laws. So you can watch this video though. It's a really good video, and it talks about these different elements and how much each part of the body is made of. So what are the building blocks of elements? Atoms. Atoms make up elements, and atoms are composed of smaller subunits called protons, neutrons, and electrons. All atoms are considered electrically neutral. The number of protons, which are the positive, I'll show you again, are these positive subunits here, are positively charged, and they always equal the number of electrons, which are the negatively charged particles. And then neutrons have no charge whatsoever. An ion is an atom that has lost or gained an electron. So if you have lost an electron, then you're called an ion, or if you've gained an electron, you're called an ion because you are now a charged atom. The atomic number is the number of protons in the nucleus. So if you look at carbon, carbon has 6 protons in its nucleus. And that number, the number of protons, actually determines or dictates the type of atom that you are. The atomic mass is the number of protons and neutrons together. So down here you see that atomic mass, and it's never going to be just a straight up number like 12. It will be 12 point something or 10 point something, and the reason for that is because the number of neutrons can vary. There are variations within an atom, and those variations all add up, and then we average out the mass. And so the mass is actually 12.011 for carbon. This is a typical planetary model for an atom, and this is usually how I'll draw my atoms with protons, neutrons, and electrons. The reason I do that is because it's the easiest way to understand where the electrons are. Electrons do not stay in one spot. We have electron orbitals, so in this one there's 2 orbitals. The orbitals actually are just areas where we can put electrons that we can show that, hey, there's electrons here. But electrons are actually continuously moving around the nucleus, so they're orbiting in different ways. So here we have a hydrogen atom, which contains 1 proton and 1 electron. Here we have helium, which contains 2 protons, 2 neutrons, and 2 electrons. And here we have lithium, which I just showed you, 3 protons, 4 neutrons, and 3 electrons. You notice that the protons and electrons always equal each other, which is why all atoms are chemically considered neutral. But an isotope is an atom that has a different weight than its normal atom. So it has the same number of protons, which means it's still the same atom, and it has the same electrons, so it's not charged. But the different number of neutrons makes it an isotope of the normal molecule. Dudley. Sorry about that. So here you have a hydrogen, which has 1 proton and 1 electron. Here we have deuterium, which is a form of hydrogen. And when you have heavy or hard water, you actually have D2O, not H2O. Deuterium has a weight of 2, this protons and neutrons together, so that this one has an atomic mass of 2, whereas the normal hydrogen has an atomic mass of 1. And then all atoms have an isotope that is radioactive. And so here we have tritium, which has 1 hydrogen again and 2 neutrons. So tritium is the radioactive form of hydrogen, and this typically what radioactive elements will do is they will decay until they become something else. Well, there's nothing really smaller than tritium, except for the hydrogen atom. So when it gives off its radiation, it's trying to lose some of that, weight, you would say. So here's your chemical symbols. Here's the atomic number. If you look at the mass number and the atomic weight, they slightly differ. So the atomic mass number is the actual number of, like, if you just add the protons and neutrons of the most common form of an element, that's what that mass would be. Whereas the weight, the atomic mass weight, is the average of all the different isotopes of the atom. And then over here, this is just talking about how many electrons are in the last or the outermost shell, called the valence shell. So what is a radioisotope? I told you that radioisotopes are the isotopes that are the heaviest form. They are typically unstable forms of atoms, and they like to decompose until they become more stable. And as they decompose, they give off radiation. So we use this to help us trace different molecules through the body. Think about if you've ever had to do an MRI, if you've ever had to do certain types of scans where they're looking at your blood. They might make you drink something first. In both cases, when you drink something, they're using certain types of radioactive materials to allow it to get through your system so that they can follow it and they can determine how it's moving through the body. When they do an MRI, they're using radiation to take a picture of that whatever body part that they're looking at. So radioactivity, though you think of radiation as really bad, most people do, it can be very beneficial. I'm going to stop here, and we'll talk about molecules and compounds in our next video. Bye.